and we are in the middle of the second to last one, finite element differential form. So the problem we're trying to solve now is that the microphone is off, and we'll solve that problem. So now we can move on to the next problem, which is if we have the Rham complex, we want to make a finite dimensional subcomplex where the spaces are finite element spaces, and it should have bounded cochain projections, and then we can apply the general theory and everything will converge. We can use them for mixed finite elements. And we were doing this and we needed a new tool. So how do you build a finite element space? Well, you triangulate the domain. On each triangle you specify a space of polynomials, and then you specify the degrees of freedom. And we were inventing a new space of polynomials that I call PR minus lambda k to accompany the space PR lambda k of polynomial differential forms. So let me try to remind you of that. We ended up with the Koszul differential, which was a tool we're going to use for this. The Koszul differential takes a differential k form and makes a differential k minus 1 form of one higher polynomial degree. And it's just contraction with the identity vector field. In coordinate terms, it takes dx sigma 1 through dx sigma k and kills each of the d's in turn and takes the alternating sum of them. So the dx sigma I becomes x sigma I, which is where you get the extra polynomial degree. In R3, that encapsulates in one operator the operations of taking a scalar 3 form, multiplying it by the vector x to get a vector 2 form of 1 degree higher, crossing with x to get a vector 1 form of 1 degree higher, and dotting with x to get a scalar 0 form. And it has a property that kappa composed with kappa 0, so we have this complex here, which is called the Koszul complex. By the way, I learned from Pascal Azarad that Koszul passed away in January 2018, and I read his obituary. He's quite a guy. He was a member of the Bourbaki group. He was the president of the Math Society of France, and he was active till very recently. And he's considered a father of information geometry as well. His thesis, though, was he was a student of Henri Cartan, and his thesis was on cohomology of Lie algebras, so he should have been at this meeting. And the one major property of this Koszul operator, which is relatively elementary to prove, and as Ari said last time, if you know Cartan's magic formula, it's a direct consequence, is that if you take a differential k form, which is homogeneous polynomial of degree r, homogeneous, and you do d to raise the polynomial, the form degree and lower the polynomial degree, and k to go back, and then do them in the opposite order and add them, you get back u again times a constant, which is r plus k. So that's a calculus identity. In any one particular case, you could prove it by hand. It's many calculus identities in one. For example, this is one. I'm sure you know this by heart, right? The curl of x cross a polynomial vector field is x times the divergence of the vector plus x times the divergence of the vector field is the vector field of back again times the degree plus 2. Crazy calculus identity. Okay, what can you do with this? What can you do with this homotopy identity? Well, the first thing you get for free is that this Koszul complex is exact. Because suppose kappa u equals 0, well, u is equal to 1 over r plus k times kappa du plus d kappa u. But kappa u is 0, so this is gone, and that shows that u is kappa of something else. Kappa of 1 over r plus k du. So that shows if kappa u equals 0, implies u is kappa of something. So that's an exact complex. More important for us is the second relation. Let's take the space of homogeneous polynomial of degree r k forms. Then according to this, it's equal to kappa of something plus d of something else. This space is equal to kappa of polynomials of one lower degree, forms of one higher degree. Kappa maps this space into here, and d maps forms of one higher polynomial degree but lower form degree into here. And this formula proves that this sum is onto. And it also proves the sum is direct, because if something is both a kappa and a d, then d of it is 0 and kappa of it is 0, so it's 0. So we have a direct sum breaking up the homogeneous polynomial of degree r k forms. Now let's look at polynomial of degree r k forms. This is equal to polynomial of degree r minus 1 k forms plus homogeneous polynomials of degree r. Polynomial of degree r is polynomial of degree r minus 1 plus a homogeneous polynomial of degree r. But the homogeneous polynomial of degree r have two pieces, these guys. So I can put these here. So let me cross this out and put in these two pieces. Okay, so I've broken up polynomial of degree r into polynomial of degree r minus 1 and two pieces, a kappa part and a d part. If we throw away the d part and only keep the kappa part, this space is by definition PR minus lambda k. So PR minus lambda k sits intermediate. It's between PR lambda k and PR minus 1 lambda k. It's strictly between these two things, except in two cases. In the case of n forms, when k is equal to n, then there are no, in the case of n forms, then there are no kappa terms, because there's no n plus 1 forms to come in. Kappa takes n plus 1 forms to n forms. There are no n plus 1 forms, so this term would be gone. And so in the case of n forms, we would have PR minus lambda n is nothing other than PR minus 1 lambda n. In the case of 0 forms, then the d term isn't there for, the d term is not there for a similar reason, and so we haven't thrown away anything. So in the case of 0 forms, we would have equality without changing the index. PR 0 is the same as PR minus 1 lambda 0. Remember, for 0 forms, we're going to use Lagrange elements. That's why you haven't heard of two families of Lagrange elements, because they're equal. For n forms, we're going to use discontinuous Galerkin elements, all polynomials of degree r with no continuity. Again, there aren't two families of that because they agree with each other. It's just an indexing change. Okay. So now let me tell you what the finite elements are. So what finite elements to use for k forms. You pick the polynomial degree you want. You pick whether you want to use the PR lambdas or k's or the PR minus lambda k's. And then you can define them this way. You take your triangulation. For shape functions on each triangle, you pick either PR lambda k of t or PR minus lambda k of t. Any r you want greater than or equal to 1. And then here are the somewhat amazing formulas for the degrees of freedom that you use. So they look a little scary, but in fact, I'll try to show you that they're very systematic. And I mean, if you know mixed finite elements, if I was to ask you, if you haven't studied this exterior calculus, but you'd study, say, the Bretzi-Fortin book or Bretzi-Fortin Bofi book, and I say second order BDM elements, what are the degrees of freedom? Very few people can write them down because it's hard to remember. They're a little confusing. They're different in different references and so forth. Here it's much more systematic. So what do? Well, the first thing to notice is something a little surprising. When you want to explain what the degrees of freedom are for the full polynomial space, PR lambda k, you use weighting functions to compute the moments which are in PR minus, or P something minus lambda d minus k. And vice versa. Here when you have PR minus, here you use PR. And now where do those crazy indices come from? Let's do one case. Let's do the case of PR lambda k. I want to explain what degrees of freedom. Remember, that means for every u in PR lambda k, I want to make a functional associated with each face, f. I want to have a functional. And I want to do this for all faces of various dimensions to be specified on the triangle T. What am I taking the moment of? I'm taking the moment of the trace of u to the face f. That already has some information in it because the trace of u is the trace as a k form. For 0 forms, that's just the restriction. For 1 forms, that's the tangential components and so forth. Now, you look at this and you say, well, what kind of object is u? Well, it's a k form. So what's the trace of f of u? Well, that's a k form on f. The trace of a k form is a k form. And what's f? Well, f has some dimension. If f had a dimension less than k, this would be, if f had a dimension less than k, this would be a k form on a space of dimension less than k. That would be 0. There are no forms of higher than the dimension. So that means we have to start off with d greater than or equal to k. Otherwise, we would get 0 here. There is no, the trace would go to 0. So that's why we start with d there. When we have 0 forms, we start with vertices, but with 1 forms, we don't have any degrees of freedom on vertices, just on edges. Okay, so let's look at the case of d is equal to k first. Let's take that case first to get us started. So now we have a k form, and we restrict it to a k-dimensional face. Well, that's integrable as it stands. I don't have to do anything to change it. But suppose I had d greater than k. In that case, this is a k form, and I'm trying to integrate it on a space of higher dimension. You integrate k forms on k-dimensional spaces. You integrate d forms on d-dimensional spaces. So I have to take this k form and turn it into a d form, so I can integrate it on a d-dimensional face. How do I turn a k form onto a d form? Well, I multiply it by a d minus k form, where the multiplication is the wedge product. So I should do that, and this q should be a d minus k form. So over here, I should take q in d minus k forms on f for all f, a face of dimension d with d greater than or equal to k. So those things I put there, they're not arbitrary, they're forced on us so that the whole thing makes sense. Okay, then the final question is what polynomial space I put here. So there's one thing I don't know how to explain, is this p minus. Since we're doing p here, you do p minus. That's the way it works out. I don't know a good intuition on it, so that I have to remember. Okay, and what degree? Let me write this with a little more room here. Q and p minus. And then I have to fill a degree here. And then we'll be done. Then we'll have described what the degrees of freedom are. Well, the trace of u on the lowest degree faces, the faces of dimension k, that's a polynomial of degree r on a face of dimension k. That's just a scalar function. It's just a polynomial of degree r. And we want that to be continuous. We want to have some continuity from one to another. So I should have polynomials of degree r when d is equal to k. But that should be all polynomials of degree r, not polynomials of degree r minus 1. But that doesn't matter, because these are d minus k forms, which is 0 forms when d equals k, and 0 forms, there's no difference between pr and p minus. So that's the right degree, polynomial of degree r when d is equal to k. And then you remember, like with Lagrange elements, as you raise the dimension of the face, the weighting functions go down in dimension. So I should have subtract a d plus k, add a k, subtract a d minus k. So when d equals k, it's r, and then it goes down as we raise d. And that's the formula. So it's basically forced on us. That's this formula up here. And you can do the same thing for pr minus lambda k. You just have to remember that the weighting functions are in pr, and you get this formula. very similar formula, which actually had been discovered by Hipmeyer in one of the papers that had a lot of influence on me in '99. This creates piecewise polynomial differential forms with the right amount of continuity such that the exterior derivative makes sense. In some cases the curl makes sense, in some cases the div makes sense, whatever it applies. So that's it. Those are the key finite element families. They're completely defined now. Now I want to take those finite element spaces and make subcomplexes of them. There's one subcomplex for the PRs and another subcomplex for the PR minuses. And how do they work? Well, the PR0 forms, if you take D of them, are PR minus 1 forms, and you take D of them and so forth. And we have the right continuity, so we can apply the D. So this is a finite element de Rham subcomplex, this top one, decreasing degree PR forms. The PR minuses, it's a little different. The PR minus, remember, is PR minus 1 plus the kappas, but without the Ds. So when I take D of it, well, it's between PR and it's between PR and PR minus 1. I take D of it, I get down at least as low as PR minus 1, and PR minus 1 is contained in PR minus. So D takes PR minus lambda 0 to PR minus lambda 1. I don't have to lower the degree. I have the elements I need here, and so forth. So this is another possible subcomplex. Then the next question we should ask is, do these subcomplexes have bounded commuting projections? That was the last property that we needed, and if they do, then we can use these for the abstract Hodge-Laplacian and so forth. So how would I get a projection from a real 0 form into a PR lambda 0 finite element? Or how would I get projection from a continuous 1 form into these 1 forms? Well, we've defined degrees of freedom, and when you define degrees of freedom, that gives you projection operators. And you could ask, does the projection operator with these degrees of freedom commute with the exterior derivative for some reason? And that's nothing other than Stokes' theorem applied again and again and again. So Stokes' theorem says that the projection operators associated with these degrees of freedom give us commuting projections into these complexes, which is exactly what we need. That's one of the reasons we use these degrees of freedom. And now, if you're really being careful, you'll see that I've stepped over 1 point. See what it is? I needed bounded commuting projections, and I just explained why we have commuting projections. I didn't explain why they're bounded. And the answer is they're not bounded. For example, the most famous of these is just P1 lambda 0. That's piecewise linears with values at the vertices, and evaluating of a smooth function at a vertex is not bounded on H1 by Sobolev embedding theorem. So then there's some technical stuff where you have to smooth it before you project it, and then you have to correct it because it's no longer a projection and so forth. That gets a little technical. But on the basis of these unbounded commuting projections, we can build bounding commuted projections. And then finally, there are some more complexes that mix together the PR minuses and the PRs. If you understand these two, you can get the other ones fairly easy. I won't mention them. But it turns out that if you want to solve the, say, 1 form Hodge-Laplacian, and you use 1 forms from this space, and as your sigma variable 0 forms from this space, that'll be stable. And that's all the way across, and same for the next one. So you can use PR lambda k minus 1 and PR minus 1 lambda k, or you could use PR minus lambda k minus 1 and the same PR minus lambda k, or you can mix them together in these 2 ways, and those are all stable. And so now we're done. We've come up with our finite elements. We've proved from a general theory that they give us convergent methods that work for all these problems, Hodge-Laplacian, Hodge wave equation, eigenvalue problem, and so forth. And here they are on one chart. And let me talk a little bit about what they are. So this is the PR minus family. In one dimension, the first three polynomial degrees, 1, 2, and 3, in 2 dimensions, and in 3 dimensions. In 1 dimension, you have 0 forms and 1 forms, and that's it. In 2 dimensions, you have 0 forms, 1 forms, and 2 forms, and that's it, and so forth. And what are these? Well, of course, the 0 forms, they're just the Lagrange finite elements that we know and love. So that's Lagrange. For 2 forms, they're just discontinuous polynomials, complete polynomial spaces, constants, linears, quadratics, constants, linears, quadratics, but discontinuous. So those are the DG elements, discontinuous Galerkin. And that leaves these other ones. Well, those ones are the ones used for 1 forms in 2 dimensions. These are the Ravi-Artoma elements, or rotated Ravi-Artoma elements, that have had an unbelievable impact since their discovery in 1975. And then Ravi-Artoma elements were getting to be very important, and by 1980, Nedelec figured out how to generalize them to 3 dimensions, and he was smart enough to realize that they had to need 2 spaces, one for H div and one for H curl, because div and curl are very different in 3 dimensions, while they're very similar in 2 dimensions. So the Nedelec face elements were the one for H div in 3 dimensions, and the Nedelec edge elements were the one for H curl. So these constructions have just rediscovered these spaces and systematized them. What about the PR? That's the PR minus spaces. What about the PR spaces? Oh, sorry. There's one other guy who got into this business. He only did the case of PR minus spaces when R equals 1, but he did it in 1957 while he was doing topology, and that was Hassler-Whitney. Had no idea as far as there's no sign that he knew anything about finite elements or he even had heard the term. I don't know. Probably not in 1957. But there's beautiful geometry in the P1 minus lambda 1s. For the 0 forms, there's 1 degree of freedom per 0-dimensional vertex. For the 1 forms, there's 1 degree of freedom per edge. For the 2 forms, there's 1 degree of freedom per face. And for the 3 forms, there's 1 degree freedom for triangle, for tetrahedron. So there's a huge amount of geometry in there. And he was using them for things like proving de Rham's theorem. By the way, in his book, he realizes that these things will have a problem if, when you refine the mesh, the tetrahedrons get long and thin, and he gave an n-dimensional proof of how you could refine a mesh without having degeneracy, which was discovered by finite element people decades later and proved and reproved many times. Here's the PR lambda K family. So you just get the Lagrange elements again, no different, and you get the DG elements with the only difference the indexing is perturbed. But here's a new family. These are not the same as the other ones. This family is Bretzi, Douglas, Marini in 85, with Bretzi and Marini sitting here, and Douglas being my advisor. And then when they came out, Nedelec immediately got to work and said he had to get the Nedelec elements of this type, and he got the Nedelec face elements of the second kind and the Nedelec face elements, edge elements of the second kind. Now what I should do now, Gerard Awanu will be disappointed with me because I should now move on to cubical elements, and he and I were some of the contributors to that, because in that, this nice systematic one had some holes in it. We had to discover some new elements. But you might have seen this. Aria had a copy, so I have one with me. The periodic table of finite elements. Actually, this is the small version. There's a bigger one. You can see it looks, well, we'll skip that. It looks like this. Everything I just showed you is there. The PR minus family, the PR family, and these are the 2 families that are analogous for cubical elements, somewhat analogous. And all the information about them is here. And I still have some of the large ones available, so if you'd like it, give me your postal mailing address. I'll mail it off to you. Okay, any questions? We're done with finite element differential forms. Mr. Licht.
You just have this name Sullivan on the slide before.
Yes, I jumped over one of the greatest living topologists, Dennis Sullivan. He has a paper on rational cohomology theory or something like that, a fairly difficult paper, where it is defined on an arbitrary triangulation in n dimensions the space of full polynomial differential forms with exactly the continuity that we're talking about here. And perhaps I should mention Garth Baker, who was a talented numerical analyst who actually decided to switch to be a topologist, and it's through one of his papers that I learned of Sullivan's work. He had ideas of doing this and using them to compute eigenvalue problems and things like that. Any other questions?
Johnson-Mercier for the lowest degree. Johnson-Mercier for the lowest degree.
You're talking about an elasticity element.
Yes, but it was based on this approach.
Okay, we'll talk about it. Okay, now I want to close the lecture by talking about a lot of complexes and a lot of applications. I have two goals in mind. One is convincing you that it's not only the de Rham complex, there are other complexes, and it's worthy of having a theory. And two, how to use the complex to do numerical analysis kind of things. So this is something I've learned fairly recently. We would have done finite element exterior calculus slightly different if this had existed at the time we were doing and we had known about it. This is a very powerful theorem by Martin Costabella and Alan McIntosh, where they deal with the de Rham complex, but not the L2 de Rham complex and not the C infinity de Rham complex, but rather a Sobolev space de Rham complex with a variable degree S. And they show the following thing. Take the de Rham complex, 0 forms goes by D to 1 forms, goes by D, etc. to N forms, and pick any Sobolev index you like, positive or negative, or integer or not, and start at HS lambda 0 and drop down degrees with each D. This obviously forms a complex, and they claim it has the exact same cohomology no matter what S you choose, and it's the same as the C infinity case and the L2 case. In fact, you can represent the cohomology independently of S, in the sense they said for each of these spaces there's a finite dimensional subspace, which is contained in the C infinity subspace, because it's contained in all the Sobolev HS's, independent of S, which represents the cohomology of this complex, in the sense that the null space of D is just the range of the previous D plus exactly this finite dimensional space. So the cosets of this guy mod the range give you all the cohomology. So it turns out, and they prove this using pseudo-differential operator theory. It turns out this is a very powerful result. One thing you get immediately, once you know that this is finite dimensional, that means the range is finite dimensional, that means the range is closed. And range is closed is very useful. That leads to Hodge decomposition, harmonic forms, lots of, all the stuff we need for our theory. In addition, well, of course, the cohomology spaces are independent. That's what they did. It has closed ranges for all S. It leads, by a very simple proof, as a consequence of that, you get a regular potential. So if F is D of U, then U can be taken to be, if F is in L2, U can be taken to be in H1. You get a full lifting of the regularity. And from that, you get a regular decomposition. So these are very powerful tools. You can write any differential form in L2 with D of it in L2 as D of an H1 plus an H1 left over. You have a compactness property. So the main takeaway I want to have from you, if we can prove the existence of complexes in this Sobolev form, and we can do it sort of independent of S, then we get all the properties that we need to do finite element exterior calculus with the complex. Okay, so other complexes. Okay, so the de Rham complex is good for a lot of problems, Hodge-Laplacian, Maxwell's equations, div-curl problems. But now there are other PDEs out there, and some of them are handled by other complexes. So the 3D elasticity complex we saw before, here I write it in the C infinity case. This first operator, the deformation, that's the symmetric gradient of a vector field U. So it takes vector fields to symmetric matrix fields. Then the incompatibility operator is this curl T curl Sanvenant operator, curl of the rows followed by curl of the columns. That keeps things symmetric matrix fields, and their divergence gives you vector fields. So that's one of the important complexes we want to derive. We want to show it's a Hilbert complex, and then we would like to get finite element subcomplexes with bounded cochain projections. Here's another one, the Hessian complex. So the Hessian complex starts with a scalar, takes the Hessian, gets a symmetric matrix field. Like the elasticity complex, we have a second order operator there, and then the other two here are first. Takes symmetric matrix fields, the curl is a trace-free matrix field, and the divergence is a vector field. So that's another nice complex that comes up, for example, in solving the biharmonic. Also, some other applications. Then the div-div complex is a little bit adjoint to the Hessian complex. It ends with a second order operator, but it starts with a vector field going to the deviatoric gradient. What does that mean? It means take the vector field, take the gradient, and only keep its trace-free part. And then you take take the curl of that and symmetrize it, and that gets a symmetric matrix field whose divergence is C infinity. And we have also, when I write down these complexes, I'm implying all sorts of things, like a trace-free matrix field has a curl which is skew symmetric if and only if its div-div is equal to 0, and so forth. Lots of stuff is being implied by these complexes. This one has applications to plates and has been pushed quite a lot by Dirk Pauli and Walter Zulainer. Also to the Einstein equations, and one of my students wrote his thesis on that, Vincent Cannaville-Belair. And numerous other ones. And I'll show you how you get complexes like this and try to make it more systematic. So I'm going to give you a construction which starts with two complexes that we already understand, like maybe the Rham complex, and derives a new complex which inherits properties from the old two complexes. For example, we'll be able to derive the cohomology of the new complex in terms of the cohomology of the old, and we'll find that the dimension of the cohomology is just the sum of the dimensions of cohomology of the old ones. And if we start with HS Sobolev versions of the original complexes, we'll get HS Sobolev versions of the new complex, and then we can use these powerful theorems of these powerful consequences of McIntosh and Costabella and McIntosh. Okay, so this is the last piece of heavy exercise. How are we going to get complexes from complexes? Okay, take a deep breath. We're going to start with two complexes of Hilbert spaces. I'm doing this in the abstract. So the Z's are Hilbert spaces, and the D's are bounded linear operators such that two D's in a row give us 0, and the same thing with tilde is a different one. But they're not quite independent of each other. The Z's have the form of some Hilbert space, tensor product, some finite dimensional Hilbert space in both cases. The idea of this is this might be a Sobolev space HS or HS minus something, and this would be something like vectors or scalars or matrices or some finite dimensional space. For example, if the Z complex was the Sobolev-de Rham complex, then ZK would be HS minus K, lambda K, which breaks up as S minus K tensored with alternating K forms. Because remember that a K form is a field with values in alt K, Rn. So an HS K field is HS tensor, this finite dimensional space that has dimension n choose K. Okay, so this and an HS minus K field would be this, so that could be my choice for VK and EK. And now we require a relationship. I want to have a mapping that goes diagonal from the tilde space to the next higher non-tilde space. For that, I need to be able to map the EKs and the VKs. And I'm going to map the VKs very simply. I'm going to assume they're equal to each other. So V tilde K is equal to VK plus 1. And the EKs, I assume these are finite dimensional spaces, and I assume that we have a map between them, little sk. And then I make a map between the tensor products by tensoring with the identity from v tilde k to vk plus 1. So now I not only have my two original complexes, but I also have connecting maps S. And the last assumption is that the connecting maps have two properties. One, of course, they commute. In homological algebra, everything commutes. Well, it actually anti-commutes with a minus sign. That's a simple matter. So I assume that SD is equal to minus DS. And the other thing is we have a property that we call capital J injectivity surjectivity. I choose a capital J between 0 and n minus 1. That is, I choose one of these S operators, and I assume that one is bijective. And the ones to the left of it are injective, and the ones to the right of it are surjective. Okay, so that's our setup. That's the input. If you can come up with two complexes and these S operators satisfy these two conditions, then you're going to get a new complex. And you're going to get it in 4 steps. Well, sorry, we've already done 2 steps. Step 1 was the two complexes. Step 2 was the S operators between them, so there's only 2 steps left. The first step is reduction. We're going to take these spaces here and make them smaller. We're going to take the E's and make them smaller in the following way. We're going to replace EK with the range of SK minus 1. So if we go over here, I'm going to replace this E1 with the orthogonal complement of the range of S0, which mapped E tilde 0 to E1. So I don't keep all of E1, I only keep the part that's in the range of little s. And I do that on the top. On the bottom, I'm going to replace the E tildes with the null space of the S going out of them. So that's what this says here. And so I have a complex that's been reduced on the top and a complex that's been reduced on the bottom. And I go out to level J here, and I start at level J plus 1 here, and then I'm going to splice this end to this end. That's the last and final step, fourth and final step. I'm mapping from here to here, from the top complex down to the bottom complex, and I do that as follows. If I start with the Jth space on the top complex, D takes me in the J plus first space in the top complex, and we assume that Sj was a bijection. So I can follow Sj backwards and get to the Jth complex on the bottom, and then D tilde takes me to J plus first on the bottom. That's how I splice the two complexes. So, did you get that?
No, what did you do with the
Okay, watch and then you can ask. Step 1, input two complexes of the right form. Step 2, put in the connecting maps. The one in red is a bijection, to the left are injections, to the right are surjections. Step 3, reduce the spaces to the left of the red arrow on top by taking the orthogonal complement to the range of the S's, to the ones on the bottom complex to the right by taking the null space of the S's. Step 4, do the boom, boom, boom using the fact that S is bijective. That's your new complex. That's about 4 hours of latexing, but okay. So that's the construction. We call that the BGG construction because it has some vague thing to do with something famous in the representation theory of Lie algebra. It's called the Bernstein-Gelfand resolution that I don't really understand. Okay, and there's a theorem associated to it. The dimension of the kth cohomology space of the new complex is bounded by the sum of the dimensions of the kth cohomology space of the input complexes. And if we make one more assumption about the S operators, that they induce the zero map on cohomology, which happens in practice, then we have equality. So we really have gotten the cohomology. And as a corollary, these things have closed ranges, and therefore we can apply most of our theory. Now you can ask a question. Answered, see? Look at that. Anything else? Okay. So now let's get some examples. How are we going to satisfy all these crazy assumptions? Well, here's the idea. I'm going to take the de Rham complex with some index s here. It won't always be s. But whatever it is here, it's one less here, and so forth. That goes from scalars to vectors. This is really HS tensor old 0, which is scalars, and this is HS minus 1 tensor old 1, which is vectors, and so forth. But I won't necessarily leave it that way. I might take 3 copies of this in 3D. In other words, I take a vector-valued version of this. So that means I tensor this with vectors, say old 1. That's one way of representing vectors. So then it really becomes old 0, HS tensor old 0 tensor old 1 goes to HS minus 1 tensor old 1 tensor old 1. And I go across the whole complex tensoring it with old 1. That just means tensoring with old 1, a 3-dimensional space, means taking 3 copies of the de Rham complex. And since we know the de Rham complex, we know its cohomology, we know 3 copies of it has 3 times the cohomology. Okay, and instead of old 1, I could have put here anything else, and I'll in general consider putting old j for different values of j. Okay, so fix a value of j, capital J, between 0 and n. For your input complexes, take the Sobolev de Rham complex, one of them tensored with old j, and the other tensored with old j plus 1. So the one tensored with old j looks like the de Rham complex hs lambda 0, hs minus 1 lambda 1, blah, 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 tensored with old j. hs lambda 0 tensor old j goes to hs minus 1 lambda 1 tensor with old j goes to hs minus 2 lambda 2 tensor with old j, and so forth. And then the one below is exactly the same, except it's old j plus 1 at the end. And then remembering that hs lambda k already has a tensor in it, that means that the vi's are the hs minus i's, and the ei's, well, on the top they're old I tensor with old j, and on the bottom they're old I tensor with old j plus 1. Then I have to come up with that was step 1. Step 2 is come up with the connecting maps, the little si's that take this space to the next one of these spaces. Takes old I tensor old j plus 1 to old I plus 1 tensor old j. Now what does that mean? Well, old I is a multilinear form that eats I vectors and spits out a number alternating in the that's skew symmetric in the I vectors. And old j plus 1 is the same kind of thing with j plus 1 more vectors. So together the tensor product takes I plus j plus 1 vectors, and it's skew symmetric in the first I and skew symmetric in the last j plus 1. That's what this is. It's a tensor of rank I plus j plus 1 with certain symmetries. This is a tensor of rank I plus j plus 1 also, but it's skew symmetric in the first I plus 1 vectors and the last j vectors. Well, now if you think about it, you'll think of what the map is. You want to take something that eats up I plus j plus 1 vectors, and it's skew symmetric in some things, and you want it to end up being skew symmetric in a little more things here and fewer things there. So all you do is you take the components of this tensor and you gather together the first I plus 1 of them. So you take an extra one of these L's and put it out in front. So now it's I plus 1 vectors. And you skew symmetrize. The brackets mean you anti-symmetrize. Take the skew symmetric part. So you just force the symmetry you need to get you from something whose skew properties are I comma j plus 1 to something whose I plus 1 comma j. Those are the SIs. Okay, that's sort of a little abstract. It's just simple linear algebra in Rn. But let's look at it in R3. Old 0 tensor old 0, old 0 tensor old 1, old 0 tensor or old 1 tensor old 0, old 2 tensor old 0, old 3 tensor old 0. That's just scalars, vectors, vectors, scalars, because old 0 doesn't do anything. It's just scalars. Now it's old 0 tensor old 1. Well, old 0 doesn't do anything, but old 1 is vectors. Old 1 tensor old 1, that's vectors, tensor, vectors, that's matrices. Then vectors, tensors, and vectors, and so forth. And we get scalars, vectors, vectors, scalars, vectors, matrices, matrices, vectors. Same thing again, vector, matrix, matrix, vector, and then back to scalar, vector, vector, scalar. And we have diagonal maps going up the way I just discussed making them. The first one maps vectors to vectors, and it's nothing, it's just the identity. The second one maps matrices to vectors. What is that one? How do you turn a matrix into a vector? Well, one way to 3 by 3 matrix. One way to do it is look at only the skew symmetric part of the 3 by 3 matrix. That has only 3 components and line them up as a vector, the right signs, so-called axial vector of the matrix. So we call that the vector skew. It takes the skew part of the matrix and turns it into a vector, thinks of it as a vector. That's the second map. The third map takes a matrix and ends up with a scalar. Well, you would guess what it is, the trace. What else? The next one takes a vector and ends up with a matrix. Well, it's the reverse of V skew. It takes a vector, thinks about it as a skew symmetric matrix, that's the matrix, and so forth. So these are all the S operators. So now, if I take fields with values in these finite dimensional vector spaces, going across the way, I have a de Rham complex, a regular de Rham complex, a vector valued de Rham complex, and so forth. And I have connecting maps. And I have lots of choices because I can pick one from one row and one from the other row. So let's do it. There I have a vector valued de Rham complex, a scalar valued de Rham complex, a vector valued de Rham complex, another vector valued de Rham complex, and another scalar valued de Rham complex. So suppose I pick the first 2 rows. This was step 1 and step 2. We have the 2 rows and we have the connecting maps. Step 3 and step 4 tell me this is, oh, we have to check if that's a bijection. Well, that was the identity from V to V, so that's a bijection. By the way, you notice we have the bijectivity. If you check it, the red guys are all bijections, and the green guys to the left are injections, and to the right are surjections. This S1, you might wonder what it is. That's the operator that takes a matrix to its transpose minus the trace times the identity. I don't really know why it's that matrix, but it is, and that's a bijection in 3D. Okay, so I take the first 2 rows, I get a new complex. And here is what you get, is a new complex. Well, you did a D to go across here, then you did an identity and another D. And these are the first Ds, so they're both gradients, so this is grad, grad, so it's Hessian. That's how the Hessian comes up in the Hessian complex. And this is symmetric because of the reduction operator we did. This operation here is the skew one, and we get rid of the skew one, so we end up in the symmetric, or sorry, it's the null space of this guy, which is the skew, so we end up in the symmetric matrices, and so forth. So that's how you get the Hessian complex. If you want to get the elasticity complex, you use the second 2 rows. Then the bijection occurs in the middle. You do the reductions here and here. And here you get curl, then you get this S1 operator and curl, and that turns out to give you the inc operator. And finally you get the divergence operator. You can do the last 2 rows. You're dying to see the last 2 rows now, right? Which the bijection comes over here. The second order operator comes from a div. That's the identity div, so we get the div. And the reductions give us things like sim curl and dev grad. And now you think we're done, but we're not done, because we could do 1 and 3. 1 and 3, then you go through a double S's in S, and those 2 S's make the identity. And so we get this one, that gives us the grad curl complex. And so now you know that we can do 2 and 4. And am I done? 1 and 4. So you get that one, which gives us the grad diff complex. So in 3 dimensions, you get all those complexes, and you get all their properties and stuff, just knowing de Rham. So all comes out of de Rham in this construction. But we're not done, because now I got more complexes, and I can try to use those complexes to make more complexes. By the way, this is all joint work with Kaibo Hu, and many of these things I'm saying were his realizations, especially this iterate the stuff that came from him for completely. So here what I did is I put the elasticity complex on the top and the div-div complex on the bottom, and these are the connecting maps, and that leads to something that gives us a third order tensor. And you know you're on the right track because that tensor has a name. It's called the Cotton tensor by a guy named Cotton. And it occurs in relativity and some other places. We're trying to understand it. The first operator here is the deviatoric part of the strain tensor, the trace-free strain tensor. And now let me just give you one application of this. Whenever you have a closed Hilbert complex, you have Poincare inequality. What's the Poincare inequality at this level here? At this level here, it says vector field is bounded by its deviatoric strain tensor. That means a vector field is bounded by its symmetric gradient, but you don't need the whole symmetric gradient. You only need the trace-free part. It's stronger than Korn's inequality. For the elasticity complex, that would be Korn's inequality. This is a strengthened Korn's inequality that holds in 3D. And it's interesting, it doesn't hold in 2D, and this construction doesn't get to this complex in 2D, so it works out well. Okay. And now I want to start to, any questions? Now I want to say some things discrete. Elena.
Complexes have a different differential equation.
What's that?
Generate different PDEs.
So every one of these, you take any one of these complexes like this one, and you pick any one of these spaces, it has a Hodge-Laplacian. So at this one, it would be a curl, 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 curl Hodge-Laplacian, because you'd have to take the adjoint of this. That's a fourth order curl problem. At this level, you would get the Hodge-Laplacian that had to do with grad div and 4 curls and so forth. And some of these are very important equations, and some we don't know where they come from, if they are important or not. For example, the elasticity complex gives you elasticity, but it also gives you something related to Einstein at a different level.
But do you have some complexes that you understand all the PDEs and you know how they are related to each other?
Well, the Rham we know completely, right? We get the standard form of the Laplacian, then we get the Hodge-Laplacian related to Maxwell's equations and with magnetic boundary conditions and so forth and so on. We doing pretty well with the elasticity complex, but some equations are more important or better known than others. Okay, let me do this also in 2D, mainly because I want to show you in 2D the discrete stuff. So I'll rush through the non-discrete because it's easier in 2D than 3D. We start with 2 Rham complexes. In 2D, you could write the first operator as curl rather than grad, and the last operator is div rather than curl. And this one is scalar valued, and this one is vector valued, and these are the connecting maps, and that leads us to this operator here. This is the divergence of a symmetric matrix. That's the equilibrium equation in elasticity, and this is the curl-curl, which is called the Airy potential function in elasticity, in 2D elasticity. That's the Sobolev version. This is the L2 version, the one that we use for finite element exterior calculus. And then the question is, how could we choose finite elements in here, here, and here that make a nice complex? And the idea is going to be, we'll do it up, we know how to do it for de Rham complexes in many different ways using PR and PR minus spaces. So we're going to carry out this crazy construction on the discrete level using finite element de Rham complexes, running them through the 4 steps to get out something for the new complex. So this is what you come out with. I have to take 4 spaces, H2, L2, symmetric matrix fields, and then vector fields. Then H2 we already, sorry, I have to take, that was the top row, H2, H1 vector fields, L2, and then the H1 vector fields will use the same thing in both places, but then I have to do L2 matrix fields and discontinuous vector fields. And these are the things I'll choose. For H2, I'll use the Argyris-Quintic space, which is the simplest known finite element in H2. For H1, I'll use the Hermite-Quartic finite element space, which is a somewhat complicated element that you see here. For L2, I'll use not quite discontinuous P3 because I'll enforce continuity at the vertices only. Why this complex? Because this complex works for the de Rham complex. How do I know that? Because Falk and Nealon studied it when they were studying the Stokes complex. Because de Rham, when you start with H2, is sort of useful for Stokes. And then this is H1. So this is a nice complex with known finite elements. Then we'll use the same thing down here because we want to have equality over here. We want the S from here to here to map it to here. And this one was the tricky one. What finite element can I choose so that its skew symmetric part ends up in this space? And it's a variant of the Bretzi-Douglas-Marini elements, but that has continuity at the vertices, which was suggested by Ralph Stenberg for vector valued problems, and which I'm using 2 copies of now for matrix value problems. So this is a matrix valued Stenberg element, and Stenberg paired that with discontinuous piecewise quadratics. And this all fits our hypothesis, and therefore we can reduce and splice, go through our steps, and we end up with this complex here. So this is now a complex, subcomplex of the elasticity complex in 2D, curl, curl, div. It uses the Argyros element for the H2 element, the reduced Stenberg element, where we've only taken the symmetric part for this space, and discontinuous Galerkin 2 for this. And this is a good elasticity element. And this is one that was proposed recently by Jun Hu and Shengyu Zhang in 2015. They didn't get at it this way. They got at it as a sort of variation of the first element for mixed elasticity, the Arnold Winter element in 2002. Falk wasn't involved with that. And that's the first time we started using complexes to make finite elements, and we used our gyros here. And here we used a different space, and theirs a little bit smaller. On the other hand, theirs is the full P4 space, ours is a partial space, and we're lower degree than theirs, which is either better or worse depending on how you think about it. Anyway, now these are sort of complicated finite elements, and we have good reason to believe, or maybe prove, that any finite elements that work for these complexes will be complicated. So we looked for a way to solve elasticity that wasn't so complicated, and we went back to an idea that went to the engineer Frias de Voybuck way back in '75, where he took the elasticity equations, which would be A sigma t plus U div t equals 0, div sigma v equals f, and he put it in extra Lagrange multiplier term to enforce skew symmetry, to enforce symmetry. So here he did not assume the stress tensor was symmetric, and then he made it orthogonal to skew symmetric guys to make it symmetric. That can be studied with complexes, slightly different complex. You have to include the skew part as an extra term in the operator. So if you take this little complex and you do the Hodge-Laplacian for it, you get this formulation. Now we'd like to show that's a good problem, so we want to show there's no homology, so we want to show anything here is in the image of something here. So what it means is we have to show that any vector field can be written as the divergence of a matrix field, and you can give the skew part of that matrix field arbitrarily. How do you prove that? Well, you use the construction and the complexes. So that's what we want to prove, that this is onto. And this thing comes from these 2 complexes and these connecting maps. So now what do? I start with the thing I want to hit over here and the thing I want to hit over here. So my goal is to find a matrix field whose divergence is V and skew part is Q. How do I do that? Well, the bottom complex is exact, so I can certainly find a matrix field whose divergence is V. That's just the de Rham complex. So that gets me that. The problem is the skew part of rho won't be Q unless I'm very lucky. So I take the difference, Q minus the skew part of rho. But then the top complex is exact. So Q minus the skew part of rho is divergence of something, psi. But then S is an invertible operator. So I can pull psi down to some phi, which is a matrix over here. And then I can take the curl of phi and use the fact that this is commutative or anti-commutative. So let's see here. So the skew of the curl of this will be, the skew of the curl of phi will be the same as the div of the S of the phi, which by construction will get me to be Q minus Q rho. So what have I done? This rho already had divergence V, and I added a curl to it, so it still has divergence V, and you follow around this diagram, and you see that its skew part is also exactly Q. So that's how you use this construction to get properties from the de Rham complex to properties for other complexes. And now I'll end up, then what we wanted to do is the same thing on the discrete level. This was done by Falk-Winter and I on mixed finite elements for elasticity with weak symmetry. We did the discrete version of these same complexes and found out what properties the finite elements had to have, and came up with finite elements that are not very complicated, and showed that these were good finite elements for elasticity. And this is the last slide, just a picture. Again, remind you, why do we care about good mixed finite elements for elasticity and these other things? They have many good properties that other elements don't have. So this is a very standard engineering benchmark problem. Take a elastic rectangle with some holes in it, put it under tension. You get large stress fields here and here, but this large stress field was computed with standard finite elements, just not mixed finite elements, and it looks pretty ugly. And if you blow it up right around this hole, you can see that it's oscillating on the size of the mesh. You redo the same calculation using mixed finite elements, and you get the ones that we discovered through that process, and you get a beautiful picture. So it really makes a difference. And I will stop there.
Do you have a systematic? So you build up your new Hilbert complexes out of the de Rham complexes in your example. As I understood, you first have the complicated Hilbert complex, and then you try to write it as the sum of other complexes in order to know how to get this very good discretized complex, because you know how to discretize the de Rham complex. Do you have a systematic way of, if I give you a Hilbert complex, how you would try to write this, the sum of de Rham complexes?
No, we don't have that. We haven't really come at it that way. So it's more like every now and then we bump into a Hilbert complex, like when dealing with elasticity, we bumped into the elasticity complex. And then we don't know how to prove its properties, like it has closed ranges and things like that. And then we realized that if we can, so it is sort of like what you said, if we can reduce it, put it in this framework, we could handle it through the Koszul-McIntosh kind of results. And then I realized at some point this idea of these S operators with alt J, alt I cross tensor alt J, and we saw what you could get, and we got a whole bunch of complexes, including elasticity. But now if I get some other complex that doesn't show up there, well, first of all, there's no guarantee it comes from de Rham complexes. Maybe it comes from something else altogether, and we don't know how to do it. It is true, I guess, that all the complexes we have now are either one level or two levels of iteration of de Rham complex. But that might be our personal weakness. I don't know.
Okay, so you don't have an example of a uniquely...
We don't have a prime factorization of complexes or anything like that.
That would be nice, right? Because then you can build up...
Get to work.
Any Hilbert complexes.
So bring paper for the train ride home. Harry.
So I noticed at the beginning we were talking about the de Rham complex, you had these spaces like H lambda k. But then when you started doing the derived complexes, you switched to the Sobolev de Rham complex, which with the HS lambda k.
Right.
That's why you ended up with those nasty things like H2 where you need to use Argyros elements. Is there any way of doing this derived complex without having to
Well, for a long time, I didn't know to use these HS spaces, and I didn't know the Costabel-McIntosh results that you get the same cohomology if you do. And I kept having trouble with the S operators because they weren't bounded. So you have these unbounded S operators, and they didn't seem to fit. It didn't feel like it fit so well. So then we tried to do it at the C infinity level, but it doesn't work for finite elements. So the HS seemed to fix this problem. So I think it's the way to go.
Any more questions?
Let's go.
You never discuss, you never have a problem with stability of your mixed element because it's built in the complex structure. You don't need to check if subcondition.
If you have a subcomplex with bounded cochain projections and you solve the Hodge-Laplacian, it's guaranteed to be stable, where the stability constant only depends on the bounds on the bounded cochain projections. That's the theorem. So that's why you don't have to talk about it. It handles all the stability of all these things at once. It handles the pure mixed cases that Bretzi's theorem handles, but it also handles the Hodge-Laplacian that don't fit in a Bretzi structure. Yeah.
In which publication can I find the elements which are used in the slides?
For elasticity, well, this is
Especially incompressible.
mixed finite elements with weak symmetry. Arnold Falk-Winter Math Comp on my webpage.
So maybe we should move on to the last one, and thanks Doug for